Right now, you and this whole galaxy are being pulled across space. We named the thing we thought was doing it. Nobody has ever seen it with their own eyes, and the name was wrong. Look up tonight, far from a city, and you will see what hides it. That pale band across the sky is not a view. It is a wall, blocking about 1/5 of the sky in visible light. So what is behind it? You have probably heard what is supposed to be back there. Some kind of monster, a black hole big enough to drag whole galaxies toward it. 3 errors in that sentence, and 40 years to find them. Here is the first error, the small one. Whatever is out there, we are not falling toward it. We are going past it. We miss it by 30 degrees or more. You have never felt any of it, and you never will. No wind, no shudder, nothing to push back against. Falling and floating feel the same from the inside, which is why a pull this big can stay invisible. It had to be caught from outside. Everything on large scales is drifting apart. That part is settled. But the drift is not clean. Every galaxy also carries a small motion of its own on top of the expansion, and that little extra is the whole story here. Usually those extra drifts point every which way. Local tugs, local neighbors, noise. Average enough of them together and they should cancel out to nothing. That assumption is where the trouble starts. There is one way to measure this absolutely. The oldest light in the universe looks very slightly warmer in one direction, cooler in the other. That difference is not the universe being lopsided. It is us moving. One measurement, and you are the thing that moves. If you want more of these, subscribe. A group of astronomers, back in the 1980s, measured hundreds of them across both hemispheres. On the standard picture, the answer should have been noise, cancellation, nothing. That is not what came back. The drifts did not cancel. Across an enormous stretch of sky, hundreds of galaxies were leaning the same way at once. Something was organizing them, not one or two. Enough of them, together, to leave a pattern the noise could not make. It gave the source a name before anyone had any idea what it was, the Great Attractor. 40 years later, the name has held up better than any of the answers. That monster is still the answer you will hear most often. A supermassive black hole, sitting in the dark, eating the neighborhood. It is a good story. It is also the second error, because when the region was finally mapped, nothing you could point to was massive enough to be doing the pulling on its own. No monster, just a crowd spread out. What is out there is a shape. A broad, shallow, flat-bottomed dip in the pull of gravity itself. Not a thing sitting in space. A slope that space happens to have. Rain does not choose the valley. It just follows the shape of the ground. Every galaxy in this part of the universe is doing the same thing, running downhill on a slope nobody can see. Water stays in a valley. This flow will not, and that will matter later. If galaxies run downhill, the bottom should be heavy. And you are on that slope right now. Not in some abstract way, and not just your galaxy. The whole local group, our galaxy and its neighbors with you inside them, is moving at about 630 kilometers every second. That is Boston to Washington, every second, toward a patch of sky no one ever taught you to look at. But how do you weigh something you cannot see, cannot approach, and can only detect by watching everything around it move? A dip that's shallow, spread that wide, still needs something heavy at the bottom. The first estimate put that at about 10,000 trillion suns. That number sat in the textbooks for about 20 years. Then a different kind of eye reached it, X-rays. And that is the third error. 9/10 of the mass was not there. Picture weighing a mountain and finding most of it was never on the scale. The revised figure came in at roughly 1/10 of the original, measured through the dust with X-rays instead of estimated around it, which leaves a problem. 1/10 of the original mass, on its own, cannot bend the slope this far. Something else has to be involved. So the question changes. Not what is out there, but how much of it we can see at all from behind that band of dust. There's something strange about that discovery that usually gets skipped. Those astronomers never actually saw the thing they named. They could not. It sits low against the band of light, buried in the dust of our own galaxy. There was nothing there they could photograph in visible light. So they measured them one by one. 469 galaxies, each one done separately, each one worked out against the expansion. Then they followed the arrows, extended outward. The drifts pointed to the same patch of sky, a patch they could not see into. 7 astronomers published it. The field started calling them the 7 Samurai, and the name has outlasted every version of the answer so far. Which means the discovery everyone remembers as finding something was really the opposite. They did not find an object. They found a direction, and then argued about what belonged in it. That argument is still going. And the reason it is still going is sitting right in front of the answer, which brings us to the wall. Our galaxy is a flat disk, and we are inside it, looking out through the crowded plane of it. Dust absorbs the light. Stars crowd the frame. Together they close that stretch off completely, like driving with part of the windshield painted over. Astronomers named that region, with no ceremony at all, the Zone of Avoidance. For most of the history of the field, it was simply where extragalactic astronomy stopped. Stand outside for a second and take that in. The widest thing in the night sky, the one you came outside for, is also part of the reason we still cannot see the last of what is pulling us. The view is the obstacle. Getting past it took a different kind of looking, not better telescopes. Infrared for the dust, radio for the gas, X-rays for the heat. Each one blind to something, and each one able to ignore what stopped the others. And when they finally looked behind the wall, nobody could say in advance what would be there. A void, a crowd, or nothing that explained the flow at all. The blank space on the map had never been blank. In 1996, a massive cluster surfaced out of the dust, in the patch the arrows pointed to, and it had been sitting there the whole time we were calling that part of the sky empty. The emptiness was ours. And then an entire supercluster found in 2016. Not a galaxy, not a cluster, a supercluster hidden behind that same band for all of human history. Generations swept that patch and never saw the supercluster sitting behind it. So the wall came down, partly. The cluster at the bottom of the slope turned out to be Norma, and it got a mass and a place in every diagram. For about a decade that looked like the end of it. But the mass they could find was not big enough to do the job. Add up everything visible behind the wall, and the numbers still come out short of the pull that is moving you. That gap is where 4 decades of work went. Then one of the original discoverers came back. Alan Dressler published again this year on the same region he helped discover, with a ruler accurate to 5%. And in his account, the Great Attractor was never the hard problem. It was the smaller of 2 problems, and the larger one had been growing quietly while holes opened in the wall. The claim was that the drift does not stop, that it keeps going, far past our neighborhood, out to distances where the standard model says it should have all but died away. On those scales, the standard model allows only a small residual drift, and this one is far bigger than that. A drift that size at that depth is not a detail. If it holds, the model does not need adjusting. It needs a piece it does not have. A team put a number on it in 2023 using cosmic flows, the largest catalog of galaxy motions ever assembled. 428 kilometers per second, and everything out to that depth is drifting together. Run the standard model 100,000 times, and a flow that big shows up 3 times. And if it is right, the Great Attractor stops being the answer. That result traveled. It is the reason for the headlines, the ones saying the local universe is breaking cosmology. And it is exactly the result Dressler set out to test with a sharper ruler. His argument is not about what is out there, it is about the ruler. Picture a tape measure that is off by 1/5 of a mile on every reading, sometimes long, sometimes short. The tape is not broken, it is just blunt. Out here, that scatter is bigger than the drift they are trying to measure. The defense is volume. Measure thousands of galaxies and the noise averages out. But that needs the noise to stay even. When the scatter is bigger than the signal, averaging does not clean the measurement. The errors tilt one way, and averaging locks that tilt in. So Dressler used a sharper ruler, one that reads distance from the grain of a galaxy's light, about 4 times more accurate. With that ruler, across the patch of sky they could cover, the drift does something the headline surveys never showed. It slows down. And at around 70 megaparsecs, a bit over 200 million light years, it stops. Sit with that for a second. If it is right, nearly all of the pull moving you comes from a volume we have already mapped, and so do you. No crisis, no missing giant, your whole address on one page. 2 teams, 1 question, opposite conclusions. One says the drift runs to the horizon, and that cosmology has a hole in it. The other says it stops nearby, and the hole is in our instruments. This is not settled, and I am not going to pretend it is, so set both teams aside. There is one check that does not need either of them to be right. Map every galaxy out to a few 100 million light years, add up all their gravity, and you can predict which way we should be moving. That prediction gets about 87% of it right. That sounds like success. The trouble is the direction. Predicted and measured sit about 21 degrees apart, and the candidates for that gap are all where we cannot check them. Almost right is the most uncomfortable result in science. It tells you the model works, and that something real is still missing from it. One candidate for the missing piece is not a thing at all. It is a hole. A region behind us, emptier than average, some 700 million light years out. And an empty region pushes, which sounds like it breaks physics. It does not. Nothing pushes from the empty side. There is just less pulling from it. Picture a tug of war where one side simply has fewer people. In one analysis, that difference accounts for about half of our motion. So much of what moves us may not be a thing pulling harder. It is an absence, a shortfall that adds up like a mass. And it was found the way the attractor was found. No telescope ever showed the thing itself, only what it does to the flow. When they mapped that side, there was far less there than in the volume around it. That is what an absence looks like on a map. And some researchers push that further. The local universe is not one attractor and one void, but dozens of both, so the 2 names are shorthand for a crowd, which is the same correction we already made, 1 scale up. In one accounting, counted by region instead, the famous one comes out smaller than its name, 44% of our motion. The rest is attributed to structures much farther out. Nearly every candidate answer has been narrowed, corrected, or taken away. Most of the motion is accounted for. 2 questions carry the rest. Which structure is doing most of the pulling, and whether our measurements reach far enough to tell. Another answer, published the same year, came from a completely different direction. Not from measuring harder, but from running the universe forward. A team built simulations of our actual local universe, not a generic one. They started from the galaxies we can see, tuned the model until it reproduced the motions we measure, then let it run far into the future. That is a prediction, not a measurement, and it is worth exactly as much as the tuning behind it. Present-day flow lines tell you which way things drift now. Future trajectories tell you where they end up. And here's the part that is easy to miss. Everything these simulations follow happens long after you, on a clock where your whole life would not fill a single frame. And the first error comes back here. We were never heading for that patch. We pass it, wide, which always left more than half of our motion pointing somewhere else entirely. The simulations were asked a blunt question. Over the whole future of this region, which single structure moves us the most? It is Virgo, the cluster we have been able to see clearly the entire time, high above the dust, no wall in front of it. 40 years spent looking behind the curtain, and the structure that ends up moving us most was standing in the open. Other clusters contribute, but at a fraction of Virgo's level. The region that got the famous name turns out to be a channel the flow passes through, not the place it is heading. And the reason nobody caught this earlier is not carelessness. Present-day velocities are all anyone could measure, and for 40 years they were the only thing on offer. The instrument that could answer the other question did not exist yet, and it is a computer, not a telescope. One paper, one method, this year. Not the end of the argument, but the newest move in it. The same simulations do something to the Great Attractor itself, and it is hard to state gently. Follow real trajectories instead of present-day flow lines, and it thins out, then drops off the map. Stiskilec's team published that this year. Nobody disproved it. Nobody moved it. It behaves like a feature of the snapshot rather than of the universe, and in those forward runs it simply does not appear. Which is a strange thing to say about something with a name, a mass estimate, 40 years of papers, and a permanent place in every documentary you have ever seen about the local universe. And that changes the last question. Not what is pulling us, but where all of this ends up. When do we get there? We have been described as falling toward something, in one version or another, for the entire history of the measurement. The simulations run forward until the universe is 100 times larger than it is now, which is far enough that the answer is not a matter of patience. Across all of that, the local group closes the distance to Virgo by a little over 4 megaparsecs, roughly 14 million light years, out of a gap far larger, and then it stops. It stops because the space in between is growing. The gap opens faster than gravity can close it, and dark energy is why. Remember the valley. Water stays, the flow does not. Past a certain point, only the dense centers stay bound. So you drift a little way toward it, slow down, and stay where you are. Permanently unbound. Close enough to be pulled, never close enough to arrive. Go back to the beginning for a moment. 3 errors. Not the direction we are traveling. Not a monster, but a shallow slope. Not as heavy as we thought, by a factor of 10. And underneath all 3, one more. The word attractor. It implies arrival. It implies a destination at the end of the fall. If these simulations hold, there is no arrival. Whatever is out there, whatever name it ends up with, we do not reach it. The pull is real, and the destination is not. That door was closed before anyone gave the thing a name. And none of this is really about the sky. It is about us, and about whether a field that keeps correcting itself has earned more trust or less. Some of this we know for certain. You are moving. The dust wall is real. The region is a broad, shallow dip on today's maps, and the mass was overestimated tenfold. All of that is measured, repeated, with error bars. The rest is still open. Whether the flow stops at 70 megaparsecs or keeps going more than 3 times farther, whether Virgo really dominates, and why the gravity maps, even now, point 21 degrees away from where we are actually going. So here is where that leaves you. You are on a slope you cannot see, moving without ever arriving inside a structure that will come apart. None of that is a warning. It is just the shape of the ground, and that band of light is still in the way. 7 people once measured a drift they could not explain. Nearly everything they concluded has since been corrected, from inside, by the people doing the measuring. The drift itself survived. That is not a failure. That is the part that has been working. What is known, we showed you. What is not, we marked. Somewhere out there, the next story is already unfolding. If you want the rest of this series, the playlist is on the channel.